In a darkened lab, a fingernail-sized spider crouches on a platform, utterly still. By the end, you'll know how it clears a gap 6 times its own length, and why its legs have almost nothing to do with it. The animal is a regal jumping spider, and before it leaps it does something easy to miss. It presses a dab of silk to the surface and pays out a thread as it flies. That thread is a safety line. If the jump falls short, the spider simply climbs back up its own silk and tries again, which is why a miss is almost never fatal. But that safety line is the small secret. How the spider launches at all is the strange one, and it turns out its legs are barely involved. Researchers spent weeks coaxing this animal to jump on cue, filming every takeoff with cameras that shoot thousands of frames per second. When it springs, it crosses the gap faster than the human eye can follow. No run-up, no visible wind-up, just gone. The full story of how this hunter throws itself across open space, and what actually powers the leap, is stranger than the safety line suggests. That launch is where the case begins, and the modern file opens at the University of Manchester in 2018. A team of engineers, not biologists, wanted to measure exactly how a jumping spider covers so much ground. They chose a regal jumping spider, a stocky black and white species native to the southeastern United States, and named her Kim. Training a wild predator to perform on command is not simple. The team spent weeks moving Kim between 2 raised platforms, widening the gap a little at a time, and recording every attempt with high-speed cameras. On the longest gaps, Kim launched herself roughly 6 times her own body length and landed cleanly on the far side. Scaled up to a person, that is like standing flat-footed, with no run-up, and clearing most of a basketball court. What made the engineers lean in was not the distance alone, but the economy of it. The spider seemed to spend almost no effort. Its thin legs never coiled and loaded like a grasshopper's hind legs or a flea's spring. Something else was doing the work, and whatever it was, it did not match anything in the textbook on how animals jump. What they eventually confirmed is the part almost no one expects. The first suspect was simple muscle, and for a long time that closed the case. A flea stores energy in springy pads and releases it in one snap. A grasshopper folds its long hind legs into loaded catapults. Surely, the reasoning went, a jumping spider did some smaller version of the same thing. But the anatomy refused to cooperate. A spider's legs are thin, and they lack the bulky extensor muscles that would straighten them with real force. In fact, spiders have almost no muscle to push a leg outward at all. They have muscle to pull a leg inward, and very little to shove it back out, which is a problem, because a jump is precisely a violent outward push. So the skeptics reached for other ideas. Maybe the spider whipped its legs like levers. Maybe there was a hidden click mechanism, a latch that released like a trap jaw. Maybe the early distance measurements were simply exaggerated by excited observers. One by one, the high-speed footage knocked those explanations down. There was no click. There was no stored spring recoil, no thrashing sprint into the leap. The legs extended smoothly and impossibly fast, with a force that thin muscle alone could not deliver, which left the field staring at an uncomfortable question. If not muscle, then what pushes a spider into the air? A jumping spider throws itself 6 times its own body length, and its thin legs are barely doing the work. So what launches it? The answer is blood pressure. A jumping spider's body works like a living hydraulic machine. It clenches the muscles around its body cavity and drives its internal fluid, its version of blood, straight down into the legs. That surge of pressure snaps the legs open in an instant, like water blasting through a folded hose and forcing it rigid. The high-speed cameras at Manchester caught exactly this. A smooth, explosive extension with no wind-up, no recoil, and no hidden click. The push does not come from the legs contracting. It comes from fluid slamming them open. Then the engineers noticed something else. The spider could tune the launch. For a short, precise pounce onto nearby prey. It used a faster, flatter, more aggressive takeoff, spending extra energy to strike before the target could react. For a longer gap, it chose a slower, more efficient arc that saved energy. In other words, the spider was not simply jumping. It was choosing the trajectory in advance, matching the launch to the distance. A brain smaller than a grain of sand was solving a problem a ballistics computer would recognize. Confirmation arrived from a different direction, the silk. Watch the slow-motion footage again, and you'll see a fine thread paying out behind the spider the whole time it is airborne. For years that line was treated as nothing more than a safety rope, a bungee to climb after a missed leap. It is that. But when researchers measured the thread's tension during flight, they found it was doing something far more active. By breaking the silk at the right instant, the spider adjusts the angle of its own body in midair, pitching itself to land feet first and square on the target. Separate work on other jumping spiders showed the same trick. The dragline is a steering cable as much as a safety net. Cut the line, and the landings turn clumsy and off balance. So picture the whole sequence. The spider spins its own guide wire, anchors at a beat before takeoff, launches on a burst of internal pressure, and then trims its flight in the air by feel, trusting a thread thinner than a human hair. Two independent things had now been nailed down: a hydraulic launch and a silk tether that stabilizes the flight. At that point, the engineers had stopped studying a spider. They had started reverse engineering a machine. A jumping spider is now the blueprint for a generation of tiny robots that leap instead of roll. Here is why engineers care so much. Wheels get stuck on rough ground, but a machine that can jump a clean, self-correcting arc can cross almost anything. The Manchester team studied Kim precisely because a spider does so much with so little. No motor, no gears, just fluid pressure and a thread of silk. That is exactly the toolkit a search and rescue robot the size of a coin would need to hop across rubble towards someone trapped. So the consensus in the field has quietly become blunt. The jumping spider already solved a problem robotics is still fighting with. A predator smaller than a shirt button is, in engineering terms, a self-guided jumping machine. That agreement has changed how the animal is seen. For most of a century, jumping spiders were filed away as curiosities, bright-eyed, oddly charismatic, easy to overlook. Now their takeoffs are dissected frame by frame in engineering journals, their silk pulled and tested for strength, their trajectories fed into models for miniature landers and soft robots. The spider did not change, our attention did. And the more closely the machines copy it, the wider one gap keeps opening between the copy and the original. There is still one thing no model has cracked. A jumping spider decides, inside a nervous system smaller than a poppy seed, exactly how hard to launch before it can possibly know how the landing will go. And it is almost never wrong. No one can yet say how a brain that small runs the calculation. The case stays open.